Well, thank you again for giving me the opportunity to speak about nuclear fuel cycle, a specialty, as you've seen, I have pursued for a number of years in France. So I will speak in a very French way, because we are indeed a major fuel cycle country. But I will also not forget or keep in mind that I am speaking in a renowned teaching institution, and of course also with an important nuclear chemical engineering department. For the papers we can discuss afterwards. The first slide shows the nuclear fleet of EDF in France. As you see, we operate 58 reactors on 19 sites. All the sites and all the reactors are owned by the company EDF. We use only a single technology, which is called the pressurized water reactor technology. And in that technology, we have made an important industrial effort at standardization, because it is an important safety asset. And of course, once you have been able to standardize, you can reap economic benefits. For the 900 megawatt electrical series, we operate 34 units, and you can look on the slide the total power in that series. The next series, which started in the mid-80s, is the 1300 megawatt electrical units. And of these, we did build 20 units with a total power of 26 gigawatts. Finally, between the mid-90s and the late 90s, we built 4 units of the 1500 megawatt class, which are, of course, our newest unit. And when you take all these 58 reactors all together, we have of the order of 1400 reactor years of experience, which is quite an achievement in the field of nuclear operations, of nuclear reactors operations. We also have one completely new European pressurized reactor EPR unit under construction in Normandy, in Flamanville, way up here. And we also have one project under development, also in Normandy, in a place called Penly, but this is still submitted to a governmental decree. When we speak about nuclear production in France and abroad, our first priority is safety. Safety, the sentence may sound a bit too often repeated. In the actual circumstances, it is not a priority. It is the utmost priority, with an enormous effort of engineers, of operators, of crews, performing their daily task with an increased attention. I am, of course, referring to the recent, in March, Japanese accident at the Fukushima Daiichi plant at the northeast of Tokyo. Now, since we are running those 58 pressurized water reactors in a standardized way, safety, of course, is always improved, because we always incorporate operations feedbacks of all the units within the unit class and also across the whole fleet. Production in 2010 reached 408 terawatt hours, which is of the order of 77% of the total electricity generation in France. Let me also recall that EDF generation runs not only nuclear units, but also thermal units and also hydro plants, hydraulic power plants. The Flamanville reactor has been started in 2007. and commissioning and commercial production has been rescheduled this late summer to 2016. And the second unit of EPR class should be built at Penly, provided the government continues the operation and decides so. As you know, maybe you will ask me questions, 2012 is an election year. Perspective for the future. The first thing which we have been thinking about for now 5-6 years is long-term operation of our existing nuclear power plants and extending operations beyond 40 years. And for us in France, as in many other countries, this entailed special safety reassessment processes. This safety reassessment process entails two things: component examination and also general safety upgrade of the whole plant. And the safety reassessment, periodic, is written in our French law, the 206 law, which says a safety reassessment of any running plant has to be performed every 10 years. Now, going one further point in the nuclear strategy of EDF, we come to the preparation of fleet deployment of EPRs in the time frame 2020 to 2030, and this, of course, takes into account the United Kingdom effort for nuclear new builds. And in other countries, we try to reproduce what we did in France in the 80s with a standardized fleet based on the EPR model. And we target the following countries: your countries first, United Kingdom, America, which has had ups and downs, China, a major nuclear country under development, in Europe, Poland, and I'm not sure I've spelled the name correctly. RSA stands for Republic of South Africa. I'm not quite sure of my British acronym. Thank you. If you reach beyond the 2020-2030 time frame, we participate as a company to a national effort for promoting Generation 4 reactors, and those are advanced reactors using fast neutrons, not thermal neutrons as in pressurized water reactors, but fast neutrons. But the time frame is 2040 and beyond, and the effort is basically a government effort and led by the national labs. Now, one question in the actuality which you would be due to ask me would be, what has the Japanese Fukushima accident changed in that kind of vision for reactors? Basically, we say for a company, for technicians, for engineers, it hasn't changed anything. But politically, at least in our country, it has altered the political debate about the energy mix. And remember, 2011 is a few months before a major election. It has also altered the way people think about nuclear energy in a number of countries, starting with our own continent, starting with Europe, with decisions first by Germany and then by other countries, by Swiss. But other countries are still keeping their strategy. So this is a fact which should be borne in mind and should not be forgotten. We come to slightly more technical slides for core management, because before speaking about the fuel cycle, you have to know what is happening inside your reactor core. Engineers basically use 4 key parameters for defining their fuel management. They used the burn-up, which is the amount of energy per unit mass of fuel which will be released at the end of the cycle, well, during the whole cycle. They use also uranium-235 enrichment. They use cycle length, and this is the number of months you run the unit before you have to refuel. And the 4th parameter is how much of the core you have to replace every time you open the lid of the reactor. Now, for the current fuel management in industrial units, we use an average burn-up of 44 gigawatt days per ton, with an average enrichment in U235 of 4%. Now, when you take a look at our three classes, 900 megawatts, 1300 megawatts, and 1500 megawatt units, of course, you will find some slight variations. So 900 megawatt units, only the first early 6 ones have a special fuel management with an 18-month cycle. The next 28 units, which have a different French name, CP stands for Contrat de Programme, contracted program at that time of the government. So they use a 13-month fuel cycle. And of these 28 units, we have 22 900 megawatt units which are authorized for mixed oxide fuel. For those of you who know MOX, French international acronym, means mixed oxide fuel with a mixture of plutonium oxide and uranium oxide. And with this kind of fuel, which is fabricated in a special plant in France, in Melox plant in Marcoule, we load 30% of the core. Not only do we recycle the plutonium in the form of MOX fuel, we also recycle uranium coming out of reprocessing, which still has some energy capabilities. And we do that in 4 units at the Cruas-Meis plant site, which is in the Rhone Valley. When we think about our fuel management policies, we think some kind of standardization depending on the various classes of units we run. We have been doing lots of industrial effort to promote the MOX parity fuel management and to extend it to 900 megawatt plants, so that for an operator, loading MOX or loading optimized uranium fuel is full transparency. It doesn't make any difference. Of course, it does make difference in the industrial supply, in the running of the fuel cycle plants. But seen from the operator of the plants, he has the same kind of fuel management and the same kind of fuel handling when he's loading his uranium fuel and when he's loading his MOX fuel. Now, this strategy, which is fairly substantial and which has a long turnout time, needs upgrading, improvements, and also careful watching, so that all the major steps which we will be discovering afterwards in the fuel cycle remain coherent, one step with the other. On the next, in a few slides, I will be showing minimum 12 or 13 major industrial steps. Each square on the view graph will be billions of euros of investment, and all these plants, all these fluxes have to remain coherent one with each other, and this is called coherence of our fuel cycle strategy. One last point, when you are running 58 units, you have to think industrially and worry about security of supply, but also having diversification in the supply chain. So we like competitors, or we like competition, like you do in your country, when we are procuring fuel. So we use several fuel suppliers, same as you use several nuclear operators for building plants in the United Kingdom. Strategy first. We are indeed a reprocessing country, and we are, in EDF, a reprocessing company with a fuel cycle major operator, which is Areva nuclear cycle. Now, reprocessing of spent fuel has been implemented in France from the very beginning, and we will be looking at some historical milestones in a few slides. At the beginning, in the 70s, early 70s, this was to enhance energy independence. You can ask me questions during the discussion session. At that time, the fuel cycle strategy was not yet fully established, not only for the company, but for the whole country. There was still an important fast breeder reactor program, and so being able to reprocess the fuel and have long-term supply was a major strategic decision. The current status, and we shall be seeing things about it in the slide, is transportation of the spent fuel at La Hague and reprocessing in that major plant. We think that spent fuel represents an extremely valuable energy resource. 1% of the fuel is plutonium, and of course all our plutonium is in the international safeguards, usually the Euratom standards, the European one. And 95% of the used fuel is recovered uranium, which has still some fissile content. I have listed on the view graph a figure of 0.8% as discharge of uranium-235. And the rest, which is only 4% in mass, are fission products and other higher actinides. And these are ultimate waste. You cannot extract any more energy from them. And so they have to be treated as waste, conditioned. And our major industrial conditioning technique is civilian vitrification. This process of vitrification of the fission product of the ultimate waste is one of the major industrial options for the back end of the fuel cycle. We run it at the industrial scale since 1978 in Marcoule, in the southeast of France. And we think that technically it ensures a long-term safe confinement of this very high-level waste. And you can have intermediate storage of this waste under reduced volume, pending or waiting for the geological repository, geological disposal, which we will show in our French law will come in 2025 at the earliest. Now, for the usable materials, such as plutonium, we decided, as has already been pointed, to recycle this mixed oxide fuel in light water reactors. And the first unit loaded in this way in France was at Saint-Laurent, and that was 1987. Other PWR unit had loaded MOX fuel in Europe some years before. We were not the first country to do it, but we were the first country to push it to such a high scale with the 22 units authorized and running. So for some of the units, we use reprocessed uranium, only 4 units. And also, we believe that if you think about very long-term nuclear energy, beyond 2050, 2060, 2080, plutonium will be a very useful resource, and we keep it for being able to start a Generation 4 fleet and have the fissile material for a reasonably fast expanding Generation 4 set of reactors. This is again the simple, the reduced view graph. You start with the uranium miles here. You have milling processes to extract what will become afterwards the oxides. There is a conversion process somewhere here, and uranium enrichment is performed at the industrial scale in the southeast of France. In your country, it is the Renco Corporation, which is doing this at the industrial scale. You have manufacturing of the fuel. You have the reactors. You come out of the reactors in the way I've shown in the fuel management. You go to reprocessing. So 3 streams: plutonium, reprocessed uranium, waste. Waste become waste. They are conditioned in a special way. Plutonium is recycled in a special plant, not a uranium plant, but a MOX plant. We have one in the southeast of France. And reprocessed uranium can go again to the uranium enrichment step, again to a special fuel manufacturing process, again in the reactor. And so this is an example of what we call, at the industrial scale, a closed fuel cycle. Now you see, the same view graphs becomes much more complicated. Of the order of 11 or 12 squares, each being either a big plant or a flux between 2 plants. Also, what used to be at the bottom before has moved at the top left. Sorry, but this is the way we present it. In the center here, you can still see the 58 nuclear power plants, the 58 reactors, 22 units are loaded with mixed oxide fuel, 4 units are loaded with reprocessed uranium fuels. Take a look at some quantities. spent fuel of either type of the order of 1,200 tons per year. Coming on the right-hand side, there is transportation of the spent fuel to the La Hague reprocessing plants. I will be showing a few storage pools there. And we discharge in those spent fuel cooling pools the same amount discharged from the reactors. This is 1,200 metric tons per year. Then we move to the reprocessing and take a look at the flux. 1,050 tons per year in the La Hague plants. Now, the three streams, but at the industrial scale: separated plutonium, reprocessed uranium, waste. Separated plutonium is sent to the Bellox fuel fabrication plant, and we fabricate of the order of 120 tons per year of MOX fuel assemblies, which we put once more, this is this arrow, back in the fleet on 22 units. Reprocessed units, we load only 4 reactors, and you have the figures on the left-hand side. So reprocessing now, a few words about nuclear chemical engineering. All reprocessing plants running at the industrial scale are using one single process, which is called the Purex process, for which I understand your country and maybe with the Americans were the prime initiators. It started in the, well, in these days, in the early mid-40s, American and British teams were said to work together. So first known plant was in Savannah River plant in America or United States. Also in the west part of the country, the Hanford reprocessing plant, at that time military purposes, and they started in the 50s. In this country, you started the wind-scale operation in 1953. So that is already 58 years ago, if I am correct. Now, coming to our country, in France, we followed you, but always behind. 1958 is Marcoule, the first plant, and in our language, UP stands for plutonium unit, plutonium plant, usine plutonium. So the first plutonium plant was UP1 in Marcoule. It has been stopped, decommissioned in a few phases between 1995 and 1997. Following the view graph, the slide, in 1967 we started also a unit in La Hague. The first unit, it was already the second unit of the country, and it is called UP2. So the UP2 in those days, we still had no PWR reactors in France, but we were using reactors similar to your old Magnox. And the fuel of these Magnox reactors was Magnox type. It was French Magnox, so we have a different name for them. Was reprocessed on two sites, Marcoule and La Hague, and this new plant was built for them. 1976, we are in the great process of building our first 4 PWR units. And so we start also a plant for reprocessing the fuel. And this was an oxide plant, because as in your country, for these units, it was still metallic fuel. So a new part was added to the La Hague plant. It has a French name, HAO. I will use my own language, Haute Activité Oxide, a special shop for shearing and dissolving high activity oxide, which would come out of the PWR reactors. And then we had an expanding fleet, and we also had foreign customers, same as maybe you did in this country. And so in 1976, the high activity oxide was 1976, and the next plant in La Hague was 1989, UP3 plant, and in parallel, 1994, another unit, and those two units here, each have an 800 tons per year capability. On your side, you started a new plant in Sellafield, the Thor plant, that was 1994. And on the other side of the earth, in Japan, in 2007, the Rokashomura plant, RRP, Rokashomura Reprocessing Plant, sorry, it's a bit difficult to articulate in your language, was started, and it is a slow starter. Now, these view graphs, which come from a distinguished colleague of mine, a professor in nuclear chemical engineering, French, Bernard Boulis, are slightly difficult to get. So I took it from a 2007 course he gave in INSTN in Saclay, and those were the reprocessing capacities in the world in the year 2000. So updating those kind of slides is not always very easy. Anyhow, sorry to be a bit French, we take the first line and we speak about Kojima at that time, which is now called Arriva Nuclear Cycle, and with a throughput of 1,600 tons per year, 2 plants in La Hague, and we have also quoted on the slide the cumulative throughput since the beginning till the year 2000. Of course, the name of the plant. The next line is in your honor, United Kingdom, with the BNFL company, which has now changed names. It's a different organization, different industrial structure. Technical capability of throughput 1,000 tons per year. And you can take a look at the cumulative tons processed in the year 2000. And the British plant was located at Sellafield. For Japan, there were 2 plants, of course. Before building the big industrial units with actually CA and Arriva licensing process, chemical process license, Japan decided to build a pilot unit in Tokaimura, Tokai Reprocessing Plant, which was then followed many years later. And this was a small capability plant of 90 tons per year. But it did operate, and it provided good operation and good training ground for Japanese future operators. The last great reprocessing country is Russia, with in the 2000, I believe, the corporation was still a government department called Minatom. It is now a government corporation called Rosatom. The plant is known. It is located in the eastern part of the Urals, in a region near a town called Chelyabinsk. The plant has 2 names. We call it under the name of Mayak. Mayak would be maybe the name of the locality. And the technical name of the plant is RT1. Do not ask me the Russian translation. It reprocesses mostly Russian PWR fuel, VVER fuel, and the technical capability is of the order of 400 tons per year. Lastly, but maybe you will have questions, I have quoted India with a plant in Tarapur, which I know very little things about. To my knowledge, it has a capability of the order of this one, maybe probably much smaller, or slightly smaller, I don't know quite well. Now, on this slide, we list the 3 important steps for the Purex process. 3 important strategic and technical functions. The one function is to dissolve the spent fuel, which is in oxide 4. Function number 2 is to extract and separate the 3 streams. Uranium and plutonium have an industrial energetic value and will be put once more in the reactors. Fission products will become waste. And a third function, condition the fission products waste and all other kinds of waste. Of course, at the general level, you first speak of fission product waste, but such a plant generates many other kinds of waste, which have to be taken into account. Transport of fuel assemblies between nuclear power plants, between the reactors, and between the reprocessing plant is performed by shielded cask, and I believe the slide speaks for itself. You have up here slides waiting to be unloaded in the fuel pools, spent fuel pools at La Hague, you have a cask being lowered in a pool which is way down here, and you have an enlarged view of what is happening here. Once you have transported and discharged the fuel, you put it in the pool, and this is a famous photograph, but I have added a few technical details. Length is of the order of 50 meters. You have the width, and this is slightly over 7,000 cubic meters of water, with a capability of storing 4,000 tons of fuel. This is fairly standard in La Hague. You have several units of this kind of capability. This is not the total capability of La Hague storage, spent fuel storage pools. The capability of the whole plant is much higher. And you have mechanical structures inside the pool. Those are the baskets, which you open way up here. And you open the lid here, and you put down several assemblies. And for those of you who like engineering details, you have the type of fuel assemblies you can put depending on the reactor type. Usually, as is said here, you put more boiling water reactor assemblies per basket than pressurized water reactor assemblies. You cannot speak about spent fuel pool nowadays without touching the consequences of the Fukushima accident. If you saw it on TV, you saw that there were many worries about the spent fuel at reactor sites. So the question you are liable to ask me, and I'm answering straight away, is what about spent fuel pools in reprocessing plants? So again, the situation in our country, in France. In May 2011, a request from the regulator, which we call in French Autorité de Sûreté Nucléaire, requesting further evaluation of safety of a huge number of nuclear facilities. Not only the reactors, not only La Hague, altogether the order 150 nuclear facilities, research lab, research reactors, small facilities, whatever. And of course, in particular, a strong accent put on the 58 nuclear reactors and the La Hague processing plants. Now, the major, most prioritized facilities identified by the public authorities submitted their safety reassessment reports, which has another acronym in French, ECS. They submitted it on the required date, which was 15th of September, and the authorities, the regulator, is reviewing all these reports. Now, whether you run a nuclear reactor or whether you run a reprocessing plant, you will have spent fuel pools, as you've seen. However, in a reprocessing pool, in a reprocessing plant spent fuel pool, the heat load of each assembly is fairly lower than the heat load in a reactor vessel. And this is why I have given you a few figures, as we do on view graphs, but I've been able to duplicate the heat load decrease in time. And after 2 hours in a reactor vessel, the heat load is of per fuel assembly is of the order 20 times more than the one we have here. So a reactor fuel assembly in vessel, 2 hours after shutdown, would be way up here. So indeed, it is easier to manage reprocessing plant spent fuel pools than to manage reactor vessels and also nuclear power plant spent fuels pools. Now, the line of defense in case of reprocessing plant blackout, the equivalent of, we say for reactor station blackout, SBO, with loss of heat sink, is you should preposition special pipes and external thermal motor pumps or backup diesel generators to be able to adapt water in case you start losing either the heating or the station service power. In these kind of plants, of pools, you have several ways to do this, and you have longer time in those reprocessing pools than you have in the spent fuel pools of nuclear reactors. The reaction time for a nuclear power reactor is of the order of 20 to 24 hours. for such a pool, you have several days. So things have to be done. They are being done. They are being reviewed by the safety regulator for La Hague, but they are somewhat simpler in technical details than what we have to do for nuclear reactors. Now, for nuclear reactors, we also do all these kind of things, and we have a rapid intervention force which is being set up for nuclear reactors, but also for reprocessing plants. When you look into the technical details, these two intervention forces are somewhat different. They cannot be the same because the facilities are quite different. Now we come to waste conditioning. And you see here a metallic cylinder in which you pour a mixture of vitrified glass, which is melted at high temperature, plus the fission product oxides, which are thoroughly mixed with what we call the glass frit. You have a few technical figures. They are about this high, 1 meter, 0.4, 1 meter, 0.50, whatever. They are not that heavy, only 400 kilograms. They are, of course, they are highly radioactive. And you have of the order 15% in weight of fission products. This is, of course, an important industrial process because this is the ultimate waste coming out of the reprocessing plant. Those canisters are also used for other kind of waste. When you cut into small pieces a fuel assembly, you have small metal pieces that high, metallic, zirconium alloy. You have to do something with them. So you compact them and you press them in a special shop and you put them in the same external envelope. But when you are for hulls here, when you are in these kind of canisters, they are still radioactive. You should not approach them, but they are far less radioactivity and heat content than these ones. And what do you do once you have fabricated the glass canister itself? You store it in an intermediate storage. This is a special shop at La Hague. And of course, you will notice that you can walk above. You can be within a few meters or maybe 10 meters of a glass log, a very high level waste canister. And myself, some 10 years ago, I went regularly into such a vitrification intermediate storage shop at La Hague. When you take a look at what happens below the concrete slab, the yellow and red concrete slab, you have metallic shafts, and in which you store, you pile up 10 or 15 of these canisters, and you have air ventilation, which is coming way up here. And this all happens way down here, underneath. And of course, you can send somebody in such a shop because you have heavy shielding way up here. Of course, the gentleman has dosimetry. He's a nuclear worker. I mean, we don't send tourists, but... Now, after those slightly technical slides, I hope I have some nuclear chemical engineering students or regular chemical engineering students, and lots of chemical processes in all those plants. Tens of years of research. We come back to strategy for the French case. Now, the current reprocessing and recycling strategy is an important asset for sustainable nuclear energy. First, because we have a good waste form, and we have good conditioning and good containment and confinement of the fission products of the very high level ultimate waste. Also, this enables us to reduce the volume of a fuel assembly to something which is only 400 kilograms, and I've shown you, did I say 180 liters? Yes, 180 liters for 1 reactor year of operation. So this is indeed a small volume performed at the industrial scale. Now, we also use such a strategy to reduce the quantity of stored spent fuel. Once you reprocessed 8 uranium fuel assemblies, you get 1 MOX fuel assemblies. You run it through the reactor, so you have good fuel utilization. And of course, we recycle plutonium, and we do recycle uranium. Now, the strategy is run at the industrial scale. You've seen the figures, thousands of tons handled each year in the various stages and steps, including transportation casks. The strategy is robust and flexible. You can adapt it. Adapting meaning you can vary all quantities by whatever you need, 10, 15, 20%, to adapt to a major change of industrial fluxes. And remember, this is done at the full scale, so this is not an easy industrial problem. And of course, we have plenty of time. We can run the cycle as it is for over 20 years, and we can prepare longer-term nuclear options. Also, we have a good intermediate storage of this high-level waste, and we are capable of preserving nuclear energy materials and nuclear energy resources for very long-term planning of nuclear energy. Of course, all the tools I've shown you are plans. They are not only sketches, they are not only slides, they are not only process flow sheets, they are actually running plans. One last thing still which is missing and which should be completed to have a complete nuclear and sustainable strategy is to be able to bring down in a geological repository or disposal facility those kind of glass logs and high-level waste. Now, this is indeed a very long-term project. We started in the early 90s, in 1991, and we plan to be able to complete such a project in 2025. In France, maybe we can be called Cartesian people, from René Descartes, the competitor to your Newton. We like laws. You are a pragmatic country. So 2 laws have been voted by the French Parliament. One in 1991, so we call it the Waste Act, the Waste Law, the first one, and which said to do research. 15 years of research to be able to find the best solution. Maybe the geological repository is not the best solution. This is the way people thought in 1989. So they said to the politicians, do something, tell us what should be good for the country. Not the technicians, not the engineers. They went to the political representation, to the parliament. And of course, a national politician, Député Christian Bataille, with a colleague of his, Claude Biraud, promoted this 1991 waste law. Now, the law said that there should be an underground laboratory built, and it was effectively enacted. So there was a construction permit, and there was underground work which was performed, and 205 technical feasibility of disposal in clay was established. Technical feasibility means that you have been digging a lab, but the law says that in the lab you should not put through waste apart from making some radioactive measurements. You can bring down a source and make some kind of measurements, but you cannot put through waste. But the French law says that if the geology is all right, and if the local people and the national people agree, then you can use the same geological formation to build the true industrial facility. And this is the major scheme. Each country has its own way of thinking about these. This is our French way of thinking about it. And so you see various steps. You see public debate in 2013. Both the national public and the local communities are closely associated. The process is guaranteed by the French law. And if everything goes well, if we succeed all the steps, then we can go to commissioning in 2025. Of course, as a nuclear operator, we strongly support such a long-term project because we want to have a geological repository. Now, we voted a second law in 2006. So still ongoing R&D. How am I in time? 45, still have 5 minutes? Yes? Okay, thank you. So still pursuing research, but it is written in the law that geological disposal, geological repository, will be the reference solution. So a major change. In 1991, 3 major ways of research, which can go to 3 different solutions. In 2006, in the time frame of the first law, a reference solution with the guarantees and provisions for the public, for the local communities, and even the national communities. Plenty of debates still to come. In the meantime, in between, you have seen our capabilities for intermediate storage. I've shown you intermediate storage industrial facilities for glass lugs. Other intermediate storage facilities exist for other forms of either spent fuel or other conditioned waste in France. Of course, the glass lugs intermediate storage facility is, as you say in your country, the most glamorous. And this is why I take the liberty of showing it to the British public. Financial settlements are written in the French law also, but I will skip the details. The conclusion, our first priority for long-term sustainable nuclear energy is nuclear safety, both in the reactors and also in the reprocessing plants and all kind of other plants in the fuel cycle. Acceptability of nuclear energy goes through finding true accepted solution for the waste problem. So we say we move forward on geological disposal and best use of energy resources. Of course, as I started by being myself a fuel cycle engineer and speaking in a chemical engineering school, we believe in reprocessing. Some acknowledgements. I haven't been able to present all these slides alone. I went to see one of my former colleagues, one of the greatest teachers our country, to my opinion, our country has produced in nuclear chemical engineering. He is Bernard Boulis, both at CA and INSTN, and it is his 2007 course in nuclear engineering. This is the so-called fuel cycle modules. I should not leave the stage before saying a few words about the situation in your own country. In the United Kingdom, we have the group has acquired, the EDF group has acquired a company in Great Britain, a well-known company to the English public. It is now called EDF Energy. It is a very important producer in the United Kingdom of low-carbon electricity, and it is a major nuclear operator. So we count differently. You have 14 AGR reactors and one PWR reactor at Sizewell. Slightly technical. The British people usually say one plant, and they count the plants. Sorry. 4 EPRs under development. The diamond, orange diamond here, Hinkley Point here, B, and also at Sizewell. Sizewell being already pressurized water reactor sites. Some news on the progress of nuclear new builds by EDF Energy in your country. So July 2011, approval for site preparation. First site chosen was Hinkley Point. I'm no longer familiar with England geography. I understand it is Somerset. It's a county. County, okay. Okay. A report by your safety regulator, Mr. Mike Waitman, into implications for your country on the Fukushima accident. So no reason to curtail operations of UK nuclear power plants. UK industry has reacted responsibly and in the good way, and no cause to revisit siting strategies for new projects. And by the way, Mr. Mike Waitman was chosen to lead the IAEA International Mission report at Fukushima and to deliver a report which was delivered to the complete IAEA special seminar. This was in June. It was a superb presentation. Let me still be French. He was accompanied as number 2 by a French commissioner, a gentleman called Philippe Jamet. Autumn 2011, development consent order submission to the Infrastructure and Planning Commission. I am not too familiar with the British administrative detail. I understand this is a new way of not boggling big projects in your country. I hope I am correct. And ongoing, coming back to the engineering world, regulatory approval for EPR, what we call in the technical side the generic design approval, GDA. Finally, you also have EDF Energy response to Fukushima. As I showed you, as we all do, what was going on at La Hague in the reprocessing field. One last word for the back end of the fuel cycle. I have spoken, well, no, I will not apologize. I have spoken in a very French way, because I am by birth a French fuel cycle engineer, more than a reactor engineer. For your country, the choices will be what the public opinion wants and what the political authorities will decide. Thank you.